Now, graphs are one of the most important data structures when it comes to the applications. You will find graphs literally everywhere. Okay, so what is a graph? Graph is basically a data structure which contains two things, a node and an edge. So this is an example. Now, graphs have two types. It can be directed or undirected. So what is a directed graph? Let's say a node points to a specific node, and direction in that case matters. So basically, if we, let's say we are talking about one-way roads, the direction matters. Only one side is allowed. The opposite side is not allowed to travel on those roads, right? So that is a specific thing related to direction. And undirected graphs, the direction doesn't matter, 0 to 1 and 1 to 0 is true. Now, both of these graphs have again two types, weighted and unweighted. So what are weighted graphs? Whenever we have specific weight, some kind of importance to an edge, it is known as a weighted graph. So let's say 0 to 1 can have weight 4, 1 to 2 can be, let's say, 6, and 0 to 2 can be 10. Why do we need weighted graphs? Let's take an example. Let's say I'm at Kalyan, I want to go to Borivali. There can be multiple ways. There can be multiple ways, right? For going from point 1 to point 2. And whenever you want to go to another position, whenever we are traveling, we see which road takes the less distance, which is less distance. And at the same time, we also check for the traffic jam, which one has more traffic, and we don't use that way. So those are potential examples of what weight can be with respect to graphs, because road net system a network is itself is a very big graph and example of graph. So what are the advantages of graphs? Graphs are basically very good at representing and visualizing very complex data. As I told you, as I give an example of roadways, those are really complex networks, and those can be represented using graphs. So, how are graphs represented? We will be basically talking about two ways. The first one is adjacency matrix. So basically, let's say I have n nodes. So I will be creating a matrix of n by n rows and columns, and then whenever I have an edge, let's say from 0 to 1, if I have an edge, I will be marking 0 comma 1 position in the matrix by 1 if it's uh, not an weighted graph, or we can put the weight over there, whatever depends to the application. So basically this graph we can see 0 to 1 is an edge, we can see 0 to 1 it's 1, and then 1 to 2 is an edge, we have 1 to 2 as 1, and all others are 0. So this is one way of representing the graph. What are the pros? Representation is easier. We are simply using matrix, so representation is very easy. And adding and removing an edge takes O of one time. So it's very easy to access and check if this edge exists or not. What are the cons? We are storing it in a matrix. If there are n nodes, there will be a requirement of n square. Now this is very inefficient. So it actually varies from application to application. So if let's say we have edges quite close to a square, then we can use this representation. This is comparatively better. So this is one way. Now the second way of representation is using adjacency list. So basically First we use matrix. Now we will be using a linked list kind of thing. So over here we have node 1. Now all of the adjacent nodes for 1 will be stored in a linked list. So we have 1 to 2, so 2 will be stored over here. We also have 3, so 3 will be in the list, and we have 4, so 4 will be in the list. And now we don't have any more adjacent nodes, so it will be a null structure. Then there is no outgoing edge from 2, so this will be empty. There is sorry, we have an we don't have we have an edge from 2 to 3, so there will be 2 to 3, and then there is nothing else, so we will be having a null pointer in the linked list. Similarly for 3 we have 2, and 4 we have 4 itself, and 5 we have 2. Now this is very interesting. In graphs we can have loops. A node can point to itself. Now this can be useful in many applications. We'll not be talking in much depth about this because okay, so for some reasons those are basically used in advanced computer applications of wherever we need to compile things, compilers and all. So what are the pros? Save space, which is as we can see we are not going to n square, so it saves space, a lot of space. And cons are queries are not efficient like in the matrix. We can simply you know access the position 0 comma 1 without any issue, so that is a con. Let's move on to graph traversals now. Please pay attention. BFS and DFS are very important because you will find these things in many subjects, not just one. You will find them in AI, you will find them in networking, you will find them in many other places. You will be like, "Arey, idhar bhi aa gaya." So let's begin with the first method, which is BFS, which is basically breadth first search. So as the name suggests, we will be considering the breadth first. So now for these traversals, we will be requiring a node, a starting point. Over here, we are considering A as the starting position. Okay. So in breadth first search, what we do is we traverse the node A, which is the root, and then we consider all of the adjacent nodes to A. In this case, those are B, this is C, this is D. Now we put all of those in the queue. We learned queue. We also mentioned that they are used in breadth first search. So all of these are appended in queue, and then one by one we start expanding the nodes again. So for B we don't have any adjacent nodes, so we continue to C. Now C has E and F. We append both of those in the queue as the next level, and then we go to D. Now for D we have F, but F is already covered, so we need not again go to that position. So basically what is happening over here, we first consider a level, only then we expand it to the next level. So basically we will be first traversing B, C, D, and then we will go to E, F. So the order of traversal will be A, B, C, D, and for C we will have, for B we don't have anything, for C we will have E, we will have F, for D we have F, but it's repeating, so we don't need to go there again. In case of depth first search, let's okay, so this was breadth first search. Now we have depth first search. Unlike in breadth first search, we expand one level only after one level is traversed. Over here we go to node, we cover all of the children, only then we go to the next node. Okay, so we start at A. We can traverse any of this. Order doesn't matter. We can go to B, we can go to C, we can go to D. Over here we have gone to D. We go to D. Now rather than going to C, we will be going to F. Now we go to F. Okay, so we go to F and it stops over here. Okay, So now we return back to A, we go to C. Now C has a child F, but F is already covered, so we need not go to there again. We go to E, we see no children of E, so we return back to C, back to A, and we go to B. So basically, this is how they are traversed. So the order of traversal will be A, T, F, go back to A, C, E, go back to A, expand B, and that's it. Okay, so this was graph traversal. So let's see how the code actually works. Okay, so over here we have the BFS function. We maintain the visited array because vector because as we can see we were not considering the nodes which were already visited. Okay, so we set all of them to false initially because we haven't gone to any of those, and then we have a queue for maintaining the order and the level. Now we have the starting point. We set the starting point as true and we put it in the queue. Now we create an iterator for the queue. Now while queue is not empty, we will be I keep on iterating. Now s is equal to q dot front. We take the first element which initially will be the first. We print that and we pop it. We remove it from the queue as we don't want it again. And now we loop over all of it adjacent nodes. Okay, so this is basically looping over them. If those are not visited, if those are not visited, we set them as true. That means this node is now covered. We need not go back to it again, and we put it to the queue back. Okay, so what will happen? We initially have A in queue, then we will pop out A. The queue will be empty. Now we will be iterating through B, C, and D. All of those were not visited, so we'll be marking them as visited now. And then we take B, we see there are no children. Okay, then we take C from the queue. C will be at the front. We see E and F. E and F will be put at the end of the queue. We see D. Now D is for D. We see F, but F is already visited, so we need not do anything. Then we go to queue back. E is at the front. We print E, pop E. Now we go to F, and now the queue is empty, so the algorithm stops over there. Whereas in case of DFS, so in case of DFS, we again create an array for mapping if the node is visited or not. We, in this case, we first call the function and then we move on to second node. So again, we loop over the adjacent nodes. If the node is not visited, we call this recursively. Okay, we call this function again recursively, and again it gets printed and goes to all of the depths, and finally it returns back to the original position, and the for loop goes to the next node. Again the same procedure is followed, and so on. We have the depth first. So basically A, we iterate over the elements, we have T, we iterate over the elements, we have F. We stop over here, we don't have children, we go back to A, we go to C, we see F is a child, but that is already covered. We go to E, E gets printed. Now we go back to A again, we go to F, B, and it gets printed, and finally this thing gets executed. So this was BFS and DFS. Now let's talk about the applications. So what are the graph applications of graph? Graphs are applied at so many things. So first we consider peer-to-peer networks. So if you have used some torrent or something, you will know what peer-to-peer networks are. Basically, we connect computers and we can transfer data between them. So that is one of the application. And the second application is in search engines. So what are crawlers? Crawlers are basically uh, it basically is an algorithm. It goes to a website. It takes all of the links which it finds and it puts it into the queue, and then it again expands. So basically, it creates a big network of web pages. So somehow this is how basically the the search engines work. The Google works. It basically has crawlers. It crawls over all of the sites and it indexes them for faster approach whenever you search them. So that is one thing. Then these are applied in social networking websites. We all know Facebook, Instagram. These are just very, very big networks of people. Okay, and they have really great application. They can also have really bad applications too. And let's not talk about all of that. So basically what happens is, let's say I am friend with Mihir is friend with Param is again friend with me. That creates a graph, and then Param is some connected to someone else, and using this we can find friends for me. Basically I'll be interested in friends of my friends maybe for some reason. There is another thing. Let's say we have I am interested in football. Let's say there is someone called Kaustubh who is also interested in football. So that creates a graph, a kind of hierarchy. We can cluster the nodes and we can suggest them. So that is one of the application of graphs. Then there's pathfinding, as I mentioned in the start only. Like we have multiple ways of going from one position to another position. So this is used in that. Okay, so this is one of the application. And okay, so this is basically a visualized graph of airline transportation. This basically shows us why graphs are so important. All of our sky, as you can see, is a very, very big graph of edges. Nodes can be the airports themselves. Those can be air flights going from one position to another position. And let's say for some reason there is some emergency in flight, we need to land it somewhere. So how do we find the closest airport? That is an application of graph. We have to find the shortest path. So this is just to give you an hint as to why graphs are so important, and we should be learning graphs. We should be exploring more about them.